Hey, Hotreload here. Welcome to the fourth devlog of fæge. For the past few months, I haven't just been adding new features, I've been doing something much deeper. I essentially lifted the entire house, tore out the basement, and rebuilt the foundation from scratch. A lot of what happens under the hood for fæge has fundamentally changed, and it's a change that unlocks the entire future of the project. The future being a game designed to be moddable first, with as much open source code as possible, moving away from defining everything as scriptable objects to a fully external, type-safe, hot reloadable architecture using JSON defined in OCaml. It's a big topic, and we'll get into the weeds, but I promise it's an exciting one. Let me show you the problem I was facing. Back when I started, I used to define everything with scriptable objects. And to be clear, they were great for many things. They allow for rapid prototyping and are easy to use. But as the game grew, they came with limitations. Even early in developing fæge, it became clear that scriptable objects were not the answer. They live inside Unity's ecosystem as binary assets once compiled. They are hard to read in version control and even harder to expose to external users or tools. At that point, all my entities were defined as scriptable objects, from my weapons to my equipment and even my quests. Scriptable objects are great for what they do and allow us to prototype and iterate quickly over data changes at runtime. But for this project, I wanted a system where the game's data is transparent and accessible to anyone with a text editor. This is where JSON comes in. If you don't know, JSON is a simple, human-readable file format that allows for easy data manipulation. It is widely used in many applications, especially the web, and is supported by most programming languages. But I also wanted that data to be safe, structured, and validated. I didn't want to be debugging JSON files at runtime or creating more problems that I was solving. I needed a system that could check every single entity in the game before it even runs, so at build time. A system that would ensure that all references are valid, that a character isn't trying to use a skill that doesn't exist, or that an equipment isn't pointing to a non-existent icon. In Unity, this works when using the onValidate method. I was already using it, but for complex data object relations, I thought it was getting tedious to implement and prone to human errors. When you add a new field in a scriptable object, you also need to implement that validation logic. Meaning that if you do not write this function, then you don't have validation at compile time. On the other hand, if you have a well-defined data pipeline with built-in type safety and no implied nulls, you can be confident that every object is valid. In this setup, validation happens by default. This is what I set out to achieve. This data pipeline needed to be as robust and safe as possible. This level of safety, knowing that my entire dataset is coherent before the game even loads, is a game changer. So all of this has been in my head for months and years now. And I was pushing the problem away as often as possible, but I discovered the solution when I learned OCaml. OCaml is a functional programming language. It is not extremely popular, but it is a beautiful language. I discovered it through a close friend who's lucky enough to use it daily. He showed me how this statically typed functional first language was perfect for building reliable code and type-safe data pipelines. I went on a quest of learning OCaml just to learn it. Learning functional programming, I think, just is a good thing for a developer. It expands your brain and makes you think differently. It makes you see problems and solutions from a different angle. Learning the language was Not easy at first, but it was rewarding. My friend gave me a good reference book that I read, Real World OCaml, which I paired with learning by doing. Chapter by chapter, I built my understanding of the language as I was exploring its features through a small to-do app named Todocaml. That app was my personal sandbox for exploring functional programming. At first, I was completely lost with functional paradigms. It requires that you deconstruct the predefined object-oriented reflexes that are built into your brain. Coding that seemingly simple app was invaluable for building my initial intuition. I learned the project structures, the Dune build system, the OPAM package manager, and the general syntax of OCaml. It is also when and where I encountered the ATD project, which is the centerpiece of my refactoring now. At that time, I don't think I realized how big or how useful this library was, but it came into play a bit later. The gist of it is that ATD allows you to manipulate data, serialize it, deserialize it, and much more. But at that point, that was the extent of my understanding, and I was just discovering the tip of the iceberg. But that was it. My to-do app in OCaml was completed at that point, and I felt a lot more comfortable tackling harder problems. So my friend and I, the very friend that introduced me to the language, we went onto something that is more ambitious. Similar to how the to-do app was named Todocaml, the next project was named Zamlbie, a networked multiplayer terminal-based zombie game. Like those old school infectionator shooter game where you start with one zombie and a group of humans, and either the zombies infect all the humans before the timer ran out, or the humans surviving with at least one player left. Except I'm saying zombies and humans here, but they are literally just squares. Overall, the project allowed me to handle more complex logic, how to set up preprocessors, how to use async logic in OCaml, and just generally learning from someone with more experience allowed me to cement a lot of the knowledge that I had acquired thus far. And this is just an apostrophe, but if you have the chance to surround yourself with great friends and great developers that have different views, different experiences, would suggest you to do so. That allows you to always grow and maybe somehow find a solution to a problem that you wanted to fix in your game. Not only this, but try to surround yourself with people that can give you actual feedback and true feedback. And it was during Zamlbie that ATD that we used again really clicked for me as the solution to my Unity problem. ATD, or Adaptable Type Definitions, is a multi-part project. At its core, it is a language for describing data structures. It supports various data types and structures and allows annotations. The syntax is similar to OCaml, making it easy to read and write. ATD is particularly useful for generating code in multiple languages from a single definition. It can generate type-safe code, JSON serializers, and validators for various languages like OCaml, Java, TypeScript, and Python. This means you can define your data structures once and use them consistently across your entire codebase. Even though ATD is technically independent from OCaml, it was originally created for OCaml and is tightly integrated with its ecosystem. Therefore, OCaml remains the main focus of ATD development. For OCaml, the ATD gen package generates files containing the generated types, serializers, and validators. For other languages like Java, Python, and TypeScript, there exists some public generators. However, there is no public generator for C#, so I created my own by plugging directly into the ATD library. parsing ATD files to produce C# classes and interfaces. My C# generator is tightly coupled with the way I need to use ATD in my project, but it solves most of my pain points. With these new tools, I began the long process of setting up a robust data pipeline for my game. Refactoring started one entity at a time. I converted my scriptable object classes into ATD types and migrated their data into JSON files, adding custom validation in the process. This gradual approach kept things manageable, even if it required hundreds of code changes. On the C# side, I extended the C# generator I mentioned to support the generation of class mappers and the automation of the visitor pattern for the polymorphic variants. Now, every new data type defined in ATD is instantly reflected in C#, with custom logic generated as needed. The result is a single source of truth. The ATD files define the core structures, JSON files holds the data, and the C# code brings everything into Unity. Changes in ATD propagate throughout the pipeline, keeping everything in sync. I also implemented hot reloading, so updates to JSON assets are detected via hashes and are reloaded automatically, providing instant feedback in play mode. Ultimately, the C# code loads a dataset file referencing all assets, streamlining the entire process and eliminating duplication. Let me show you how this works in practice, doing a quick demo of the workflow. I have the OCaml project on the left side, and on the right side you can see the Unity's project codebase. In the terminal, I have the watcher script running, and we have the equipment.atd file open. This file defines the structure of the equipment entity in the game. You can see the metadata, the quality, category, and so on. At the top of the file, I have the equivalent of imports in ATD. The decorators can be placed on the type itself or on the field. On the field, it can be on the type or the content of the field. I usually use the type decorator to specify the C# namespaces and imports, the field decorator to add name or type overrides, and the content decorator for validation. You can see that the equipment category is on the type namespace and represents a polymorphic variant in OCaml, and this will be converted to enums in C#. The equipment type is in the DTO namespace, which is the data transfer object namespace, which is where all the data structures are defined. When changing anything in this file, the watcher script will pick up the changes and the compilation and execution sequence. Let me add an entry to the enum. Let's say bag. The moment I save the file, it will show on the Unity side, and removing it will also remove it. Let's say add a new type, equipment secret lore. A new file will be generated in the C# project. Removing it will also remove the file. So now that we have our new type, we can place it inside the equipment itself. Now you see we have a compilation error because our test fixture is not valid anymore. Let's fix it. Now you see that the output of the watch script tells us that we have many errors in our JSON data. This is because by default, we are enforcing a value. This is not a null by default implementation, meaning if we define a field, it is required. If we want to allow null values or empty values, we need to specify it. In the scenario that the lore was mandatory, we would have a mechanism to identify which file is missing the lore definition. And we could add a lore to all of them, one by one. But for the sake of this example, let's say it's optional. Now you see everything passes. The C# script also updated, but I usually add a decorator for optional fields to make it clear that this field can be empty instead of using the C# nullable feature. To do so, I created an optional type that is very similar to the one in OCaml. Let's open a JSON file and add the lore to it. What you see here is not exactly an equipment, but an equipment entity definition. If I were to make a typo in the field name, that would be invalid because we do not accept unknown fields in the JSON, and so the validation will fail. Now, let's say that we require the lore to be a minimum length of 6 characters, and let's add a validation for it. We see that we now have a build error in the watcher script because that validation function is not defined. And we can see that there's a typo. When fixing the typo, we now have errors in the actual data that we created in the JSON due to its length. Let's update this. And now everything passes. Adding validation is as simple as that. Adding more complex validation requires a little bit more time, but overall, it is not too complex. In any cases, if you're into coding or you're just intrigued by the setup, most of the repos for the project alongside other projects are inside my GitHub and the links are in the description. As for the hot reloading part, when the change is made to the JSON, the hash of the file is recomputed. During runtime, any change are detected through a simple hash check using our dataset index file. Since the dataset file is processed at the very end of our watch script, we avoid triggering invalid reloads when making changes. Updating any number, text, images, or models triggers an update that is reflected at runtime in the game without requiring to restart the session. At the moment, this feature is only available in Unity editor mode. However, the groundwork laid here will enable asset loading at runtime in the future. While modifying JSON has been straightforward so far, handling more complex changes can become a bit tedious. As I was converting entities from scriptable objects to JSON, I had to rethink how skills were executed. From a very sequential and linear approach that I did initially, I moved to a more graph-based representation. Skill execution are now constructed of simple and composable execution nodes. They reside inside the skill entity and are represented by a graph consisting of multiple node types like sequence, parallel, requirements, delay, and so on. Execution nodes can be connected to create complex skill behaviors. This allows for custom skill logic to be easily defined and modified without any scripting. My first skill implementation were extremely tedious, especially when you have no visuals for a very deep execution tree. So I made a full editor tool for this. This React-based tool provides a visual interface for creating and modifying skills. It allows users to easily connect different execution nodes and define the flow of skill logic. It also provides a way to visualize the skill execution graph, making it easier to understand and debug. This tool is also part of my design of making this game extremely easy to modify without any complex setup. let's run through a simple example. So let's talk about the punch skill. It's the most basic attack for adventurers, but it's a great way to show how the system works. Here's the flow. First, there's a requirement node. This just makes sure that only adventurers can use the skill. Then we move to the parallel node, where a few things happen at the same time. The adventurer's movement gets temporarily locked. At the same time, animation plays, which is the actual punching motion. And finally, there's a hit sequence. This sequence internally contains two nodes. The first one waits a little bit for the timing of the hit, and the second one describes what kind of hit we're doing. In this case, damage that scales with the attack power. But the big picture here is transparency. I want these files and tools to always be accessible. The goal is to make it easy for others to contribute, add their own features, and build a community-driven ecosystem around this tooling. Up until now, everything I've shown, the hot reloading, the JSON, the skill editor, all has been running locally on my machine. But if I really want this game to be moddable and community-driven, it can't stop there. At some point, all of this content needs to live somewhere that's accessible to everyone. That's where the idea of a backend comes in. Think of it as the backbone of the project. A server where asset bundles can be stored, updated, and delivered to players on demand. Instead of just reloading files on your own computer, the backend makes it possible for anyone to pull down new models, textures, or even new skill definitions. No manual setup required. Paired with the data pipeline and the skill editor tool I've shown, this means that in the future, anyone could create their own bundles, tweak existing content, and see those changes show up directly in the game. To start exploring that vision, I built a prototype backend using MongoDB to store metadata about assets, Mini.io to handle the actual file storage, Nest.js as the server framework that ties everything together, and nginx as the reverse proxy and load balancer to keep requests fast and reliable. It's definitely more than I need at this stage, but it lays the groundwork for a system where modding and sharing content is fast, simple, and accessible to everyone. This project has been a massive undertaking. It's a big refactor, and while I don't have flashy visuals to show, I've received a lot of feedback asking for more in-depth technical content. This video is my first step toward delivering that, and this is just the beginning. This refactor is the foundation for everything else I want to build. When I test the game now, it feels solid. It's a big project for a solo developer, but I'm motivated to keep going. I want to make sure that anyone who enjoys the game or the tools has the best experience possible. This project has been part of my life for almost 3 years now. Of course, I'm not working on it full-time. I have a full-time job, hobbies, and other coding projects that could each be their own video. I even have other game ideas parked for later. If any of this interests you, whether you're a developer, a potential modder, or just curious, I'd love for you to get involved. Ask questions in the comments, join the Discord, or check out the GitHub repos and play around with the code. Thanks for watching and coming along on this deep dive. I'll see you in the next one. Bye.